In this video, we're going to look at a proof that the perceptron learning procedure will eventually get the weights into the cone of feasible solutions. I don't want you to get the wrong idea about the course from this video. In general, it's going to be about engineering, not about proofs of things. There'll be very few proofs in the course. But we get to understand quite a lot more about perceptrons when we try and prove that they will eventually get the right answer. So we're going to use our geometric understanding of what's happening in weight space as a perceptron learns to get a proof that the perceptron will eventually find a weight vector that gets the right answer for all of the training cases if any such vector exists. And our proof is going to assume that there is a vector that gets the right answer for all training cases. We'll call that a feasible vector, and an example of a feasible vector is shown by the green dot in the diagram. So we start with a weight vector that's getting some of the training cases wrong, and in the diagram we've shown a training case that it's getting wrong. And what we want to show, this is the idea for the proof, is that every time it gets a training case wrong, it will update the current weight vector in a way that makes it closer to every feasible weight vector. So we can represent the squared distance of the current weight vector from a feasible weight vector as the sum of a squared distance along the line of the input vector that defines the training case and another squared distance orthogonal to that line. The orthogonal squared distance won't change, and the squared distance along the line of the input vector will get smaller. So our hopeful claim is that every time the perceptron makes a mistake, our current weight vector is going to get closer to all feasible weight vectors. Now this is almost right, but there's an unfortunate problem. If you look at the feasible weight vector in gold, it's just on the right side of the plane that defines one of the training cases. And the current weight vector is just on the wrong side, and the input vector is quite big, so when we add the input vector to the current weight vector, we actually get further away from that gold feasible weight vector. So our hopeful claim doesn't work, but we can fix it up so that it does. So what we're going to do is we're going to define a generously feasible weight vector. That's a weight vector that not only gets every training case right, but it gets it right by at least a certain margin, where the margin is as big as the input vector for that training case. So we take the cone of feasible solutions, and inside that we have another cone of generously feasible solutions, which get everything right by at least the size of the input vector. And now our proof will work. Now we can make the claim that every time the perceptron makes a mistake, the squared distance to all of the generously feasible weight vectors will be decreased by at least the squared length of the input vector, which is the update we make. So given that, we can get an informal sketch of a proof of convergence. I'm not going to try and make this formal. I'm more interested in the engineering than the mathematics. If you're a mathematician, I'm sure you can make it formal yourself. So, every time the perceptron makes a mistake, the current weight vector moves and it decreases its squared distance from every generously feasible weight vector by at least the squared length of the current input vector. And so the squared distance to all the generously feasible weight vectors decreases by at least that squared length. And assuming that none of the input vectors are infinitesimally small, that means that after a finite number of mistakes, the weight vector must lie in the feasible region if this region exists. Notice it doesn't have to lie in the generously feasible region, but it has to at least get into the feasible region to stop it making mistakes. And that's it. That's our informal sketch of a proof that the perceptron convergence procedure works. But notice, It all depends on the assumption that there is a generously feasible weight vector. And if there is no such vector, the whole proof falls apart.